right, this section is on work. Now, work is defined as basically the distance that something goes times the force it takes to go there. So that's really it. If they're both going the same direction, work is positive. If I'm pushing on something this way, but it actually goes this way, I'm doing negative work. Like I suck at my job, I'm doing negative work. That's work. If something is sitting on the ground, whoa, come back. If something is sitting on the ground and doesn't move, there's no work. So if D equals 0, there's no work. If the box goes from like here to here, gravity, you have to think, did gravity do good at its job or did it do bad at its job? You're like, okay, gravity sucks at its job. Gravity's supposed to make things go down. Instead it went up. So gravity does negative work. If the box slides from here to here, gravity had nothing to do with that. So gravity did no work. Does that kind of make sense? So the whole idea behind work is you have to have movement in that direction, and it has to, well, be in the same direction. So basically it ends up being a dot product is where this is coming from. So it's called, you're going to see F dot, does it call it F dot dr here? It does call it F dot dr. dr. So this can be done on an itty bitty calculus level. And the reason we like the dot product is so like if this F is in like the X component, the Y component, and the Z component of a force, and I dot it with the, you know, our X component, the RY component, and the RZ component of that R vector, then the two X's get multiplied by each other, and the two Y components get multiplied by each other, and the two Z components get multiplied by each other. So does that kind of make sense? And it just ends up being like a number. Okay, this is a scalar, and it's either positive or negative. Positive means it's doing good work, it's doing what it's trying to do. Negative means it's doing bad work, it's unsuccessful at the work that it's trying to do. So, for example, if I had a box and it was like, you know, I don't know, 5, and I could break it into 3 pounds and 4 pounds, and it went, you know, I don't know, 10 feet. Okay, then the force, so I just broke the 5 pounds into a 3, 4, 5 triangle. Then the work by the force is just the 3 pounds times the 10 feet. Does that make sense? So 30 foot-pounds or pound-feet, however you want to say it, I don't care. So it's not the full 5 times 10 because only a part of the force is going in the direction of the movement. So if you wanted to think about that like a dot product, you'd have 3i hat plus 4j hat plus 0k hat dotted with the r vector, which would be 10 in the x, nothing in the y, nothing in the z. So you'd get 30 plus 0 plus 0, and you get 30. Does that kind of make sense? Okay, so that's why it's a dot product. It's a dot product because you want the same things in the same directions to get multiplied by each other. And that's how you know what kind of work it does. So, but yeah, if, like I said, with the gravity example, you know, if you're sitting here on the ground and you're going lefty, righty, gravity is doing no work. So gravity is trying to push it down. It's already down as far as it's going to go. Gravity is doing no work. In fact, if it just floats in the air, going lefty, righty, gravity is still doing no work. Okay? If it starts on the ground, or let's just say it starts here, and it goes blonk, and it ends up right where it started, then the total work done on the box is 0 because it has 0 displacement. Does that make sense? There's no work done on the box because there's no displacement. It goes no work, back to no work. Make sense? If this box is going this way on friction, friction always does negative work, right? Because friction is trying to make it stop. Friction is like, stop, stop. And it's like, no, 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 I'm not stopping. So friction always does negative work. Friction always sucks at least kinetic friction always sucks at keeping things from moving. So that would be negative work. Let's see. So if I go from here to here, gravity does negative work. If I go from here to here, gravity does positive work. If I go from here to here, gravity does no work because there's no vertical displacement. Does that make sense? So if I'm here, and then I go right here, the total uppy-downy displacement is 0, and gravity only acts in the uppy-downy direction, therefore the total work done by gravity is 0. Okay? So that's the basics of work. Okay, so the idea is that this can be done on a super duper itty bitties, which basically means an integration. And so you'll see this here. Work is defined officially as the integral along the path of f dot dr, but most of the time you're going to see it just written as like fr cosine theta, but again, this is one of those things I'm not super keen on you memorizing, because usually it'll be like, if the force is this, and the r is this, and then the theta is in between, then the work is the cosine, because that's also the definition of a dot product. But since this is an integral, that doesn't always work. So when in doubt, always go back to the basic definition of work. But if you get this that we were just talking about, that's the big, big thing about work. Okay, so work is a dot product, work done by things that move, the distance that it's gone, that's basically, yeah. So, you know, a person moving with a lawnmower, that's just, if they're going straight, yeah, so it's just, like I was giving that example before. You just break it out, and whatever component of his force is in the direction of the lawnmower, then it's just, and in this case, it happens to be cosine, because that's where the theta is labeled, you know, but it's possible, like if they labeled the theta here, and the r was here, now it would actually be sine, right? Because this is the component, f sine theta is the component that's in the same direction as r. So don't just memorize stupid formulas, because, yep, they're not always going to work. It just really depends on how things are drawn in the picture. For the purposes of this book, maybe you'll always be fine, but I would always be careful. So yeah, like this lady carrying her briefcase, gravity is doing no work on the briefcase because the briefcase stays at the same height. Okay. Anything else exciting going on here? The work by friction is always backwards. It's always bad, bad, bad. So it's actually really interesting because friction is a very special kind of force. It's called a non-conservative force. So like whenever I had that box on the ground, like here, and I did this and I was like, oh, gravity, 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 gravity. Oh, look, gravity did nothing. The total work done by gravity is 0. But if I go like this, there's negative work done by friction, and then I go back, there's still negative work done by friction, like both directions. It's not like it's doing positive work the other way and canceling itself out. Does that make sense? So this way it's doing negative work because friction's trying to make it stop, and it's not. Now friction's doing negative work again. It's trying to make it stop, but it's not. So the longer that this rolls around, the more negative work is happening. And that's a very, very, very special thing with friction, and that's why we don't have unlimited energy. Okay, so friction is one of those very special things about work that is path dependent, because the longer it takes you to get from place to place, the more friction you have and the more work you have to do to overcome that friction. Whereas with gravity, It just matters. It's not like I have more gravity over here and then less gravity over here. It's just the same. Like, look, gravity's hurting. Oh, gravity's helping. Gravity's hurting. Gravity's helping. Gravity's hurting. Gravity's helping. So you kind of have like negative work, positive work, negative work, positive work, negative work, positive work. So it comes out to be zero. But with friction, it's negative friction, more negative friction, even more negative friction, even more negative friction. So you just keep making more and more and more negative friction. It just keeps getting worse and worse and worse and worse. So friction is very, very special, and friction is path dependent. Let's see. One more thing I want to make sure that I mentioned, because I recorded this and realized I hadn't, is that the units on work. So whenever I was doing this a minute ago, I think I said foot-pounds when I was just playing around. Yeah, I was just playing around. And I said foot-pounds. So foot-pounds is what it's going to be in customary units. Now, in what do you call this? Scientific units, international units, it would again be newtons times meters, but whenever we're talking about that in terms of work, we call it a joule. Joule, and it's a joule. So it's another one of those derived units. So if you see something like 30 J, that means 30 joules, which is the same thing as 30 Newton meters.